Jai Hind everyone. Dear students, today we are going to start a topic, the introduction to the control unit, and we will start with the concept of micro instructions or instruction cycles. So, in computer world, micro operations is basically has a very simple to do and very little to accomplish. Okay, so the smallest operation in the computer device is called as micro operation. So if you see this diagram here, the smallest operation at the bottom of this tree is coming from the breakdown of the next super instruction fetch, and the fetch is a part of instruction cycle, and instruction cycle is a part of a given program. Okay, so a program under the execution in machine language is broken into instruction 1, instruction 2, ... instruction n. A particular instruction is broken into fetch cycle, indirect cycle, execute cycle, interrupt cycle, and finally one fetch cycle is broken into a group of micro operation. So this micro operation particularly performs a very simple thing and very little thing. So what is simple thing? That is, it is doing just a transfer operation. Okay, transfer, and very little means moving from one register to another register. So that is very little job. That's why it is called as very simple. And so micro operations are doing some operations which are at the lowest level of detail. So that's why these are also called atomic operations, because it cannot be go further to be divided logically below that. Even though these micro operations are done in along the cycles, but it is not the broken further than this logical unit. So what we can see is that this approach is nothing but it is a functional decomposition approach. So a given program is broken into small number of instructions. So basically a given program is a function of some instruction, and a particular instruction is broken into small functions: fetch, indirect, execute, and interrupt, and finally fetch is broken into small functions, micro operations 1, 2, and 3. So this functional approach of decomposition is required to implement a given computer organization. So a single micro operation generally involves a transfer between first category is that is transfer between registers, or between register and external devices like memory location, and the final type of operation that is called as third ALU operation. So three classes of micro operations, simple operation that given CPU can perform, or simply we can say that the CPU performs three type of micro operations. Either there is a data transfer between one register to another register, or there is a to and fro data transfer between memory and the register, and whenever the data is received in the CPU, we finally perform some operation over there. So all the operation performed in ALU is also called as micro operation. Fine. So we are basically breaking the machine instruction into a sequence of microprogram, and this sequence of microprogram is nothing but a sequence of micro instruction. Okay, so these micro instructions are further regulated through control words that we will discuss later on. Okay, in the subsequent chapter, these micro instructions are regulated through control word. Means when the control word is there, then a particular micro instruction is executed. So it's like that when this control is received, this micro instruction is executed. When a sequence of micro instruction is executed, a micro program is completed. That may be called as a fetch routine, and when this particular set of micrograms are combined together, fetch, indirect, execute, interrupt, a machine instruction is executed. That's a simple from bottom to top approach to show a execution of micro instruction. Okay, moving ahead further, we can see that these breaking of a step of functional decomposition ultimately says that who is controlling this micro instruction. So, micro instruction is controlled through this control set of binary bits that tells different hardware components like ALU and register exactly what to do at which clock. So, that is very important that micro instruction is regulated by the control word. Okay, so basically the step or state at which what particular action will takes place is somewhat dependent upon the control word. Fine. Moving ahead, you can see there is two world. One is the within the CPU and this is the outside CPU or the outside world. So, what is happening? There is a huge amount of data transfer traveling from memory to CPU, CPU to memory, and is that only transfer that is happening? No, there is no only a transfer is happening. There is a processing also being done when the data is brought to the CPU. Why? Because CPU is having a unit that is called arithmetic and logic unit. Arithmetic and logic unit takes data from the memory within the CPU and process it, and then again CPU sends that data back to the memory. Fine. Now, this process of moving huge amount of data here and there, okay, can be sequenced or can be arranged in two ways, or there is a sequence of events that are followed one after another, or there are sequence of events that may create a conflict. Okay, so we need to understand that relationship of sequence and the conflict within the micro operation, so that we can group the micro operations together in the same clock. So, simply we can say that if conflict operation are there, they cannot run in the same clock, simple. And if there is a sequence of statement that can be executed together, they can be non-conflicting, okay, and they can be clubbed together and they can be done in the same time. So, basically in that way we are saving the time for executing a particular set of micro operations. Conflicting will not execute together and the non-conflicting may be done grouped together. Okay. So, for your understanding, we can well known these two register MBR and MAR, okay, memory buffer register and memory address register. So, basically we send a address here to the memory at which location a particular data is or instruction is, or particular indirect address is, whatever we want to refer in the memory will be sent through the memory address register. Fine. Okay. So, memory address register sends the data location where the data is. When the location is reached to the memory, memory will fetch that particular data and bring it to this location MBR. Okay. Then it can go to anywhere. Here particularly in this diagram it is going to IR. Why? Because in the next instruction that we will discuss, that this data is moving from memory to MBR, then finally to instruction register. So, this step is called as fetch cycle. Okay, so what does fetch cycle means? That we have to bring the particular instruction from the main memory to the IR register. Okay, so we are bringing data from the program counter to the IR. Okay, so program counter has the current next instruction to be executed. So, before that some previous instruction has executed. Okay, so as soon as some previous instruction has executed, the current instruction is pointing to the updated PC. Okay, So at this point, the next instruction has the location address saved in the program counter register in the CPU. The program counter register has the address of the next instruction. So I have executed the previous instruction before that. So I will send the next instruction data to the MAR. So MAR is nothing, it is again a register where the address location is shared by the CPU to the memory. So CPU has sent the address location to MAR. Now MAR can be read by the memory directly. So memory knows that at particular location pointed by MAR there is some data. So memory will send that data to MDR. Data can be instruction or data, whatever. Now as soon as data is received at time T3, two things are happening. Okay, so you can see here, this is micro operation 1 and this is micro operation 2. They are happening at time T3, and this is a very good example of that. These two micro operations are non-conflicting. Okay, they can happen together. So this is data transfer from MDR to IR, and this is the ALU operation. They are not non-conflicting. So what happening? As soon as data is arriving here at T3 time, MDR is sending data to IR. That MDR has an instruction that is now stored in instruction register. And what is my duty now? That I got the particular next instruction. So I will point again to the next of instruction. So I have graded the current value of PC to PC plus 1. So at time T3, we are doing two things. One is storing the MDR content in IR because it is instruction, and also updating the PC value to PC plus 1, pointing to the next instruction. So this is fetch cycle. So you can see that how this fetch cycle is running here. You can see here the fetch cycle is running at T1, T2 and T3, three different time interval. So how this T1, T2, T3 is known to the CPU. So you must understand this CPU clock is behind that, and CPU clock is nothing but it is a sequence of pulse that is within the CPU. Okay, so what is happening? This is the first pulse. Okay, so this is pulse 2, this is pulse 3, this is pulse 4, this is pulse 5, and this is pulse 6. So it is like a wave. So pulse of wave are passing. So by designing a circuit in a digital world, we can count this pulse. So T0 becomes 1 at this point when first pulse is coming. T1 becomes 1 when the second pulse is coming. T2 becomes 1 when third pulse is coming. So basically T0, T1, T2, T3 are nothing. It is a timing signal which is being generated through the input clock pulse by a digital circuit to know that time T0 has passed, T1 has passed, T2, 3 has passed, and so on. And finally, after the task has been completed, this counter is cleared, that is clear the sequence counter. So this time is coming from this timing diagram T1, T2, T3. So at T1, PC will first micro operation will happen, T2 second set of micro operation will happen, and then T3 third set of micro operation is happening. Likewise, there is a indirect cycle, interrupt cycle, and execute cycle. Okay. Now, before going to all these three differently, we must understand the instruction cycles are executed at various interval of time depending upon what has happened previously in the first phase of cycle. So generally speaking, there is only this order that we can follow, that we will first fetch. So when the status value is 0, 0 for the sequence generation, the fetch will be done. Then we will go for 0, 1, that is indirect operation. Then we will go for execution as a third step, and at the fourth step there is an interrupt. This is optional. It may be or may not be depending upon the interrupt enable flag register is there or not. If it is enabled, then it will happen. Otherwise, it will go to directly again to the fetch cycle again. So what we can see here, that this diagram is called as flow chart of instruction cycle. So we can easily understand that I will start from the fetch, then I will fetch the instruction. Okay, if there is a indirect addressing, depending upon yes, I will go for the 0 1 cycle. Okay, so this is 0 1 cycle. Okay, and then I will go back here and start with the indirect cycle. So user can see easily this is the a cyclic pattern. Yes or no? This is a cyclic pattern. So you are starting from the same point and after passing through this path again coming to the same point. Fine. So in this way this creates a cycle. That's why it is called as flow chart for instruction cycle. Okay. Now there might be possibility that there is no indirect operation, then what I will do, I will go to 10. 10 is execute because I have data already, so I won't go for indirect cycle. So I may go this path also. If I execute, okay, based on opcode we will execute it, and after execution there are again two decision box, two decisions, yes or no. If there is an interrupt, okay, certainly if there is an interrupt, I will go again to operation 1 that is interrupt cycle. Okay, means that there is an interrupt, and if it is 0 means there is no interrupt, I will again go to the fetch cycle. If it is interrupt, I will go here, set up the interrupt process and set ICC again to 0 for the new program node. Fine. So this is the thing that we have to learn and understand for the micro operations to be understandable in terms of working of computer at the level of within the CPU. Okay. So moving ahead further, we will then briefly discuss the other cycles, indirect cycle. So indirect cycle means that if there is an indirect address code available in the instruction, it consists of 3 time unit of steps of micro operation. Data is transferred to the MAR from the IR, okay, which is used to fetch the address of the operand, and the IR is then updated from the MDR, so it contains the address rather than data. So students, we very well know that the second part of the instruction is address. Okay, fine. And since the indirect bit is set, so certainly this is not a data, not a data. So how the instruction will execute? So it will send this particular address. Okay, so IR will send the address to the MAR. So this part is fetched through IR and sent to MAR. So memory knows that at this particular location I have to bring the data, then it will bring that data and store it the MDR, and finally this address is replaced at this step. Okay, MDR is replaced by data, indirect operation, because it is not always possible to have a data within the instruction. Certainly it will have an indirect, so there will be address. Okay, so address is replaced by this data. So 3 steps. Now my question is that, is there any indirect operation in the instruction happen only one time? No, depending upon if the number of operands are indirect, okay, both operands are indirect, so this cycle will happen 2 times. Fine. Similarly, I have fetched the data after indirect, I will go for execute. So in execution, basically what happens at T time, the content of IR, okay, will go to the MAR. Okay, and basically if the some number of time units micro operation varies depending on the execution cycle, because depending upon fetch and indirect cycle. So for example here add R1X. Okay, so you can see here that this X is a location. The following execute cycle adds contents of location X to the register. Okay, R1. Fine. R1 is equals to R1 plus X. Okay, add R1 X. So this location of X, okay, it is to be brought back. So what will happen? The content of IR will go to MAR. Okay, the address part, then the memory will bring that data to the MDR. So MDR has particular data that we need to add. Okay, so it will be MDR plus R1, then finally it is R1. Execution will happen. Fine. Now, the interrupt cycle is very interesting, and this happens optionally, means it may happen, it may not happen depending upon the condition. Okay, so it happen when there is a enable for interrupt, and if it is disabled, so it does not happen. Fine. So depending upon the operating system or the monitor program, which do not want to be get interrupted by any other peripheral routines or some external interrupt, the step is skipped and the interrupt is disabled. So the program will not stop here. At this particular stage, the instruction will execute to the interrupt service routine, not to the next instruction. So what I will do, I will first save my current program execution counter, because I am working for other, and I will save this program counter to I will also send a save location where I will save this PC saved address to MAR. So the PC will be updated at the MAR location. So I have saved my current execution address, and finally what I will do, I will add the routine address, that is interrupt service routine ISR, to the PC. Now PC has the new address for the execution for the interrupt service routine program. Finally, the content of MDR is copied to the memory. Okay, because we have to send this data to memory for saving that. Fine. So in this way, the interrupt service routine cycle begins. After interrupt service routine, what we have seen in the cycle, here you can see that if it is enabled, it will start for interrupt cycle, then we will set up interrupt. So at this point, what is happening? We are basically doing these three operations: T1, T2 and T3 interrupt cycle. So the setup operation is nothing but T1, T2 and T3, because I am interrupted. So I will first save my current execution address, where I will save at the saved address, then I will load the routine address in PC, then I will save this MDR to memory location. Okay, so in this way, the whole world of CPU executes their micro operations, okay, within this cyclic process. Okay, Jai Hind everyone, and thank you for this lecture.